Good evening, everyone. On behalf of the IEEE student branch of University of Rune, I would like to welcome all of you to the final session of SparkLink 1.0. As the last session of the second phase of our workshop series on advanced digital design, I'm pretty sure today will be a very educated evening for all the participants present here. As informed, the topic of today's session is digital design using Verilog. Just like in our previous sessions, the speaker will first conduct the session for 1 hour time, and afterwards there will be a 10-minute quiz to take your attendance. You should remember that this quiz will qualify you to obtain the e-certificate at the end of this course. Today, our partner for this workshop is one of the most popular engineering technology-based companies in the country, XLR. To learn more about our partner, let's watch a short video about the products and services they provide. Once again, we are honored to have such an excellent company partner with us for this workshop today. Today also, we have an esteemed speaker to conduct this session. He is Engineer Dasun Patirage, who is a senior software engineer at XLR. He is very experienced and a talented engineer in the field of software engineering. Sir, it is really our privilege to have you here with us today. So, without any further ado, I'd like to welcome Engineer Dasun Patirage to start this session now. Over to you, sir.
So, Dishan, can you see my screen?
Yes, sir.
Okay. So last week that you had a wonderful session, I guess you learned basic about digital design using Verilog. So in this workshop, so we are focused little bit more advanced than the previous one. So hope you had the previous knowledge, even though you miss someone who is here that missed the previous workshop. I will try to do the most way that they can also understand. Okay, so let's start. Another thing, if you have any question, you can ask it in the chat. One of my colleagues also here, Sachit. So if you want to ask anything from him, also he will also answer. So no need to speak speak and turn on the audio, so you can ask in the chat. Okay. So before going to today's session, I will go through the first the small recap, the basic. So what you learned in the last session. So what is HDL? So HDL is hardware description language. So we know that we are focusing on Verilog, but the languages also like VHDL. So what is the hardware description language? So it's a language that used to describe the digital design and describe the electronic circuit and its behavior and the structure. So from these languages, we can design FPGA or the circuits itself. So one is what is FPGA. So you know, like what is FPGA and IC, different between FPGA and IC. So if we are printing from the scratch, so we are printing from the scratch, we are designing the full IC ourselves. So it's ASIC we call. Uh, so for that, we are using HDL language, and also for the FPGA programming, also we are using HDL language. So here we are focused on Verilog. So, but you know that we have VHDL also as a popular language for this kind of tasks. Okay. So let's have a small introduction. What is Verilog? So the what's the can one of organizing committee confirm that I'm audible clearly?
Yes, sir, you're clear, sir.
Okay, so is there any question? Okay, so let's continue. So what is programming? So Verilog is using to build the design and the simulate. For both, we are using simulations and the design the circuits. So main thing that we are doing using a programming language here to design a digital design is the electronic components. So what we are doing is like we write what are the logic that we need inside our circuit, and what are the electronic component and their connectivity and how it should store data. So those kind of things we are describe and writing using Verilog. So it like here you can see, so Verilog is a virtual representation of the digital circuit, the before actual binding. That means before actual physical component and the before real print or the compile into the bitstream and upload to FPG. So before that, that's Verilog is the basic representative of the our design. So you can use this digital blueprint to verify the circuit before manufacturing, because if we going to manufacturing before the testing, it will be more cost than it, and also our time is that spent for the design is waste. So we have to do the verification on those kind of things before actually do the hardware. Okay, so that's it. That's it of the basics, like you were taught previously. So here, today's flow, I will briefly describe that what are the data types that we are going to use today, and what is blocking and unblocking assignment. and what is synchronous and asynchronous logic, and finite state machine. So a very basic introduction to finite state machine, and one example from that one with using these things. And so in previous workshop also you used the VA playground. So we will provide the link that with the code in the VA playground, so you can play with. Okay. So what are the data types? So data types is used, the data types are used to store values like 0 and, because this is digital circuit, so we have 0 and 1, and if there is like if there is two connection that goes to one same data, so it's we can, so unknown or high impedance, that if it is not connected. So don't think about much about this. So basically, data type is to store data. So we have mainly two types of data type previously that we need to learn. So one is rich. So that is a storage element, like a register in circuit. So it used to store data for modeling the sequential logic mainly, like flip-flop and register. So another thing is, other one is wire. So wire is that the most of the case wire doesn't store any uh, they don't have any storage capability. It's a representation of the connection. So using connecting different, it's used for different yeah, used to connect a different component of the circuit. Like if we have flip flop and some kind of other peripheral, so we have to connect those things. We are using wire. So what is logic? There is a data type called logic to hold both of these data type. So instead of using reg or y, because it's confusing sometimes for beginners. So even you have experience that they can have also confusion to use register or y. So in that case, it's easy to use logic. So the main reason is that logic, it can either register or y. Its compiler will automatically select what it should use register type or wire type. So you can use logic here to represent any of data type, like C++, not exactly same. So, but like some language like C++, you so auto. So those kind similar to that, here we can use logic. Okay. So we'll go to blocking and non-blocking, next step of our session today. So what is blocking assignment? So blocking assignment, for the code we are using simple operator. So it's using within the procedure block assign values to variable. So in this case, blocking assignment, the value of the right hand side will assign as soon as it change. Okay. So if B is assigned into reg A blocking as soon as it change. So that's the blocking assignment. So it didn't rely on a clock. Okay. So that's what here we say. So okay. So non-blocking. So this is mainly using like when we are deciding flip flops and register kind of thing. So for sequential modeling, we are using non-blocking assignment. So in non-blocking, this is the way that we are representing. So here, when for every, it's waiting for the clock to update. So it's not updating as soon as it change. So updating value of the left hand side using right hand side value being stored at the beginning of the time step. So the value that's stored previously will update here when the clock is changed. So that's the difference between this assignment, non-blocking. Okay, so let's talk about what is the synchronous and asynchronous. So previously I told you that we have, like, if you are using clock or not, we have a different implementation. So yeah, for the non-blocking and blocking. So it's related to this one. So first we'll discuss about the synchronous, and after that we'll go to the synchronous. So asynchronous logic is that you were learned previous workshop also. So uh, the asynchronous logic operate without relying on the clock. So it change the input immediately when the input is changed. Output is changed when according to the input. So it didn't rely on the clock age. So asynchronous logic are more responsive than, I mean, it's work speed and more responsive than synchronous logic, but it's hard to debug. So it's hard to find if we have error, we can't. It's very difficult to find issues. So if we have clock, we can go through the signals and we can find where the issue is. But if it is asynchronous, it's fast, but that can be cause many issues. So here there's code example one of the asynchronous logic. So it says like if asynchronous input. So in this variable, this register got one. It asynchronous output also got one. Otherwise it's zero. So it's very simple. So it change as soon as this input is changed. Okay, so next we will go to the synchronous logic. So asynchronous logic is operate with the clock. So always it need a clock to operate. So with the positive or the negative edge of the clock, we can define whatever the edge we need to use in our design. So if it is positive edge, we have to represent it like this, post edge. If it is negative edge, we have to represent it the negative clock. So advantage of the synchronous design, so it align with the time. So it like the trigger with the time clock cycle. So it very easily we can see the signals how it goes, and we can we can do the debugging and the signal how the signal works and all those things. We can you can see in the last end of the session in our EDM background example. Okay, so synchronous logics are mostly used for the flip-flop and registers and sequencer circuit, as I told you previously. Okay, so let's discuss what is always block and asynchronous and synchronous very brief. So if you didn't get any up to this point, if you get if you have some confusion, if you want to go to back to the slides, so just forget about everything up to now. So just remember, just have an understanding of this one. So asynchronous is is with combinational logics those are not working with clock, and asynchronous logic is with the clock, and this is the simple way of implementation in Verilog. So it's you can either use assign and write the equation, or otherwise we can write the combination logic in the or less block. So what is the star mean is, so if any parameter that is in this logic, in this begin and end block, if any parameter of this block is if changed, it will trigger. But in here, so it says only percentage of clock. If what is positive edge of the clock is changed, this sequence of block will trigger and so here there is difference between this small these two. So it is it have reset also. So if we press the reset, like we need a reset button for every circuits. Like if every implementation that we are doing, we are put a reset, because if there is any thing happen, if power goes down or something, we need to have a physical reset, or it is reset automatically have to be done. So for that one, we are giving an input reset also. Okay. So up to now, if is there any questions? If there any question, you can put it in the chat. Oh, okay. So I will continue. So now we talk about data types and what is blocking and unblocking, and synchronous and asynchronous logic. So next we have to move to the finite state machine. Okay. What is finite state machine? Finite state machine it is a way to model the behavior of a system, whatever the system, whatever the logic that we are going to describe. We are putting that to in stages. So otherwise we are saying states in the behavior of the logic that we are going to implement. So we are dividing into the states. So then we are going to implement the states in the Verilog. So this state should be finite number, because hardware can't you can't implement an infinite number of things, because hardware should be defined previously before the running. You can change the hardware while running. It's obvious, no? So because if you done a circuit, you can't change with the runtime. So yeah, so what is so here just to focus on this circle. So here you can see there are ideal state and state 1, state 2, state 3, state 4, like that. For main thing is the finite state machine is there should be a finite number of state to describe the behavior of the model that we are going to describe from the well. So there are many components that we need to focus on for basic understanding. So we can say states. These are the states. So and the transition. What is the transitions that we are doing? So based on the event happening, input or the input or the events. So whatever the things happening, based on the transition will happen. Okay, so okay, so now I will take an example. So this is the example that we are going to implement in Verilog also today, and we run it in the EDA playground. So have a focus. So we are going to do is AAXY pattern detector. So what we are going to do, we are receiving a inputs stream of characters. So if we receive double A and next again A and then X and then Y. So then we say that AAXY pattern is detected. Otherwise, it's zero. Okay, so if pattern detected, we can say from our hardware to light a bulb or show the high in the output. Otherwise, it's zero. So that's this very simple example of the state machine. So here we are using like characters. Otherwise, you can detect bit patterns also 0, 1, 0, 1, 1, 1, like that. The bit pattern detector also you can write using same logic. So here I'm focusing on A, sorry, pattern. Okay. So what are the states that we need here? First one is idle. Obviously, we need ideal state to represent the initial start state of the design. Again, then so we have x, y. So first we have to detect as A, and that means state A, then state double A. So after, if we going to state state AAX, and state AAXY. So those are the states that we are going to identify for this example. I hope it's clear. Because we have a XY detector, so we have to detect every stage of one by one. So first we detect A, then A, if it is A have, then we go to double A, looking for double A, otherwise AAX, otherwise AXY. Okay, so then transition is based on the pattern that we are receiving. Input we are receiving. So don't focus on these arrows for this in this image. So it's just mainly show you the states only. Okay. Okay. Now we are trigger the transition based on the input. So we'll go in case one by one. So if it is in the idle state, so if input is A, so if you get input is A, so it goes to state A. Then here I have not shown you the otherwise cases, I mean, or else cases. So else cases I will show in the next slide. So here just focusing on if we receiving these characters on. So if we receive A, it goes to here. If we receive again A, it goes to state the AA. Then if we receive X, so it goes to state AX. And also if we receive Y, state AXY. Okay, that's simple. So what are these arrows? Okay, so this should go to idle, you may think. So you have what we have to talk about. What is these arrows for? Otherwise, it's not going to hit. So as I told you, so I'm not for I showed you the else statement. So that's why this arrow is not here. Okay, the previous arrows. Okay, let's consider you are receiving this kind of uh, pattern X, Y. So here you can see there are 3 A's. So then it is not a pattern, but you can see like if without this A, this is a pattern that we need to detect AAXY. So but first we are receiving this A. Okay, so we are going to going here. Then we are receiving this one, second A, and it goes to here. Okay, then we are receiving again A. So we already received 2 A's. So we have to stay 2-way state. We already received 2 A's. So if we are receiving again A, so we have to stay here, same state. That's why I put this arrow here to same state. Then we receive X and Y. So pattern is detected. Okay. So that case is N. Okay. So now let's talk about the second one. So it's AAX, then again AAX. So here you can see this is not a pattern. This is after this one, after this X, you can get a pattern. So in that case, first you go A, first A, then again A, and then X. You can hear X, so state X, and then it receives again A. So if he goes to this idle state, it's wrong because we receive A. So there is a state called state A. So when we receive A, so we have to go this state. Okay, so not the idle state. Again, then according to this example, it's receiving again A. Then go to state AA and X, state AX and state XY. So again, this pattern is detected. Okay. Last example here is AAXY, AXY. So here you can see like first AI is obviously detect this pattern and the reason for this error. So again, as soon as we detect this pattern, next clock cycle we receiving another A. Okay, so another A is receiving. So if we go to idle, then this pattern will be missed. So we have to go to state A again and continue from there. Okay. Hope if you're okay with the explanation. So if you have any question, put it on the chat. Okay. Okay. So this is the final pattern detector. So with the S part also, that means if we are receiving A, it goes to state A, and again A, it goes to state A, and likewise you have state AX and AX, right? Otherwise, let's say you are receiving A here, but you are receiving X here, X for some other W or whatever the value you receive here. So it goes to idle state. Okay, so it should be continuously receiving AX, otherwise X or whatever X, Y or whatever the W, whatever value, it goes here. In this state also it's A. So if we are receiving A or X, we have these two transitions. Otherwise, we have to go to the idle state and come back from the beginning. And it goes to here also. If you are receiving Y or A, you have to use this transition. Otherwise, you have to go to the idle. In this one, also if you are only receiving A, you have to go this path. Otherwise, you have to go to the idle and come from the beginning. Okay. So this is the state diagram that we're going. We will see what are the inputs and output in our example. So first one that we need is clock. I told you that we have a clock signal that need to be come because we are doing all the things based on the clock. This pattern is going for a clock. First clock cycle it receive A, then second clock cycle it receive A, and next and for the other characters. Okay, we need clock and the reset. For a circuit, we need the reset button and data in. So data in here, there is a thing that we need to reset. So it's 8-bit, 0 to 7. So we have 8-bit here. So these are 1-bit. So this is why this one have 8-bit is so we are that those are characters we are receiving. So we need to represent in XSP. So in that case, we have 8-bit for each one of these character. Okay, so every time we receiving 8 bits to represent a character A, X, Y, or other characters like that, whatever the input. So this is in data value signal. So this signal is for we have to have an acknowledgement from the receiver that this data is valid or not. Because if we receive a garbage value, this circuit should not run. So for that, if it is garbage or some fault happen, this will 0. So even here there is available data, it didn't read when input data valid signal is false. So always when you are receiving in with the clock cycle, receiving a data a x y or other character, so data invalid signal should be high to work this cycle. Otherwise, it should be zero. So there is a data out. Data out signal here is 1 byte. Data out is if pattern detected or not. That's the simple thing that we are going to do. Okay, so this is data out valid. So valid signal is for the output side. So send the acknowledgement to output side also that this data is valid. But in our implementation, this is a data out is a single it's 1 bit output, so we are not going to use this one. So because it's if it is available, it's 1, otherwise it's 0. Because so we no need to input this one. Okay, so this is a Verilog code. So don't worry. So I will go on each block one by one, so you can get understand. Okay, so this font size is, I think you can read. Otherwise, let me know in the chat. Okay, so this module is we are going to implement in Verilog. Okay. So as I told you earlier, we know that out data valid, and we have only data out, block preset, data in, input data. Okay. So this is Verilog implementation of the module of the first initial start. So module is the module that this is keyword, so that we need to use in the Verilog. So this is any name that you are going to give to your circuit. So here it's AAXY detector. That's why it's called AAXY detector. So you have signals, clock, preset, data in data valid, and data out. So all the input and outputs are defined here. Next, we have states. So so that the inside this box, we are going to implement our state machine. Okay, so this is the state machine that we are going to implement in that box. So we need to define what are the states that we have. So this is ideal state, state A, state AA, state AX, and state AXY. Here you can see all the state. Okay, and we are giving common names to its states. And so you can see here it's a logic of 5 bits because we have states. We have to store this data in a register. Otherwise, it's not a 1 bit thing. So we need more space for store these states, because if it is changing, we need it in a like numbers. So we need each case, we need number. Okay, this is 1, 2, 3, 4, 5, 6, like. Okay, so again, let's talk about the inputs and outputs. So here we have 4 inputs and 1 output. So in Verilog, we have to define after the definition of the variables and the states and those things. We need to define what are the input logics and what are the output logics. So this logic, I think you remember that I told you earlier. The logic is data type that we are using for represent wire or the register. So we don't care about its register wire, is compile it, handle it. So it's an input clock, input reset, and here you can see that the difference, because it's 8-bit. You have to define it here. It is 8-bit because this input is 8-bit long. So we have to define it like this. Data in should be logic or you register of 8 bits. So its input is defined here. Right in the Verilog here, and data valid signal and the output. It should be output should be written this. Okay. Okay. So previous slide we talk about the oldest block. In here for this example again, I will tell you what is the oldest block, how we are using it. So you can see here we have two blocks. So here in this design we have logics that should work with the clock, and also if we have any asynchronous logic we can write in this block. Okay, so if it is any synchronous logic we can write here, or if it is a asynchronous logic we can write here. So here this begin and end is the block that we are writing inside those keywords. So this here is you can give any name to that block. So here it said asynchronous block, and here the this one here, in this oldest block we are going to implement the FSM block that we discussed earlier. This is our FSM block. So this thing is going to implement inside this block. So all the things that work with the clock and the sequential logics are in here. Okay. So this is our IP that we are going to implement. So next here we have reset. So we'll figure out what is this reset and what we are going to do in the code with the reset. So okay, so here you can see, so always if positive edge block for the reset, positive edge of the reset. So if reset is happened, so we have this always block is triggered. So then again there is a if else statement here. So in Verilog you can use if else. So if reset is happened, the logic is here. You have to write here. Otherwise, if reset is done press, so other logic is written here. Okay, so someone put in the chat where we should implement our FSM block, here or here. As part of the logic or the reset part. So anyone can put it in the chat. Okay. Yeah, it's in S part. Thank you for the message. So I know that someone is listening to me. So S part is the one we are going to implement our block. Let's know. Okay, so this is the FSM block that we talked earlier. Here you can see our FSM block, the initialization. So here you can see, like in C++, you have switch case, like we have here in Verilog case, and based on the state, it will change. So here you have idle state A, state double A, state AAX, state AAXY. So you have defined all the state here. So in idle state, what are the logic inside that idle state is inside here, and what are the state A logic inside this begin and end block, and state double A this begin and end block, and the logics in the state AAX logics are inside this one, and AXY logics are inside this one. Okay, so now you see, just think you have state machine. This is the state machine. So you have this block. This block this template. Now you have to just fill what are the transition that you should do in this each state. So you have this diagram. So that's the easiness of this one. So if you have draw the diagram and the IP like this before this diagram and this diagram, so then you can write the code without any hesitation. So here you can see you have the like we have the what are the blocks that you have to include in the code, and you have to just write the logics inside this each state. Okay. Okay, hope you can see my screen. That's font size is little bit smaller. Okay, so first we'll focus on this S part only. You can see S part in here. So first one is idle state. We are in idle state. If we receive A and data is valid, data valid signal is high. The data valid here we are saying that if it is high. Okay. So if both these signals are true, so data in is A and data valid is true, we are going to state A. Okay. And state A. And next, so you see state A. So otherwise, S part is not written here because it no need, because otherwise you have to stay in the idle state itself. And then we have state A. So if we receive in state again A, you have to go to state A. Here in the diagram you can see here, in the code you can see here. Otherwise, else you have to go to the idle state. It shows here idle state. You have to go to the code. If it is if other character is receiving here, you have to go to the idle state. Then you are in the state AA. So now if you are receiving X, so you have to go to state AAX. Seen written here. You have to go to this state. Otherwise, if you are receiving A, okay, if you are receiving A, you have to stay in same state. Here it says if you are receiving A and also the data valid signal, you have to stay in the same state. Otherwise, you have to go to the idle. Okay. So next, if I hope you receive X, so then you are in the state AX. So same thing happens. So if you are receiving Y and the data valid, you are going to state AXY, the final state, and that's mean you are that mean you are receiving Y, that mean you detect our pattern that we are going to detect. So then otherwise, if you are receiving A, if you are receiving A from here, so you have to go to state A. Here you can see if you are receiving A, you have to go to state A. This one. Okay, according to this block diagram, state diagram. So otherwise you have to go to the idle state. Otherwise you have to go to the idle state from here. And then when you are in the state AAX, right, the final state, that we know that we detect our pattern. Then again, if we receive A, as I told you in the state diagram explanation, you have to go to the state A, not the idle state. So it defined here. If you are receiving A and the data valid, you have to go to state A, and otherwise you have to go to idle and wait for a A. Hope you guys get good understanding about the code. Okay. So next part. So here you can see, like I told you, you have two blocks like clock that work with the clock, like in the synchronous block and asynchronous block. So here, this one is the one that we discussed earlier. So what is this? Here it says this is a asynchronous block. So if state is changed, so it goes to this one and check what is the state. So if it is a state SAAXY, data out should be 1. Okay, that means if we are in state AAXY, then we detect the pattern and we are saying that data out should be 1. Okay, so then otherwise, default case, other in case we have to say data out should be 0. Okay, so we can implement this logic also in here. So that's not, but that's not best practice. So we have to do like all logics. We have to implement in separate always block that is more clear and more readable. Okay, so because you can say if it is in the this state, you can just say data out is 1, and here other status we can say data out 0. That kind of implementation we are not saying that's good implementation. So yeah, so before moving to the EDA playground, you can have a look at the code. So this code is this is like each part that we discussed. So you can have a look. So here the module, what are the parameters, inputs and outputs of our IP. So what are the states? And we are here we are describing is it is an input or output. And this is a like you see here state is like we are defining variable call state. Okay, logic call state, and we have to like normal program. Let's say we are using C++. So in C++, if we are defining like this type of a data type, and we have to call it and create object from that. So that part is not here. So I will show you it in the EDA program. So because otherwise you can use the state variable, because state variable is not initialized. This is states. Okay. So but you can see the flow here, the module that we discussed, and this states initialization and input output initialization, and our FSM blocks and the output block. How output is hence. Okay, I will show you the EDA playground and explain a little bit the code, full code. Okay, so can you see my screen? Can someone confirm my screen is?
Yes, sir, we can see.
Okay, thank you. Okay, so this is the way that we are the best practices. This is the way that we are implement our codes in Excel. So this is one code that write by our colleague. So here you see the module. So here we are defining the our parameters, inputs and outputs that we discussed. And if there is any global headers, we'll define under here, and any other parameters, the definitions and local parameters, and type definitions we have to. So this template you can also use. I think I will share this this code with you, so you can have a better look later. So here you can see the state initialization that I showed you earlier, and IO signals. You can see input outputs, and this is the in one this is the only the internal signal. So I told you earlier in the presentation, this state is just the initialization of the type of the states. So the states is should be initialized in the here states and get a variable of state. Then we can use that in the implementation. So this is our implementation that we discussed. Okay. So in this kind of implementations, so test this Verilog, we need to write another code called test bench. So I'm not going to discuss in detail about test bench. You can go through the code and get better idea. But because it's out of the scope of the presentation. But if someone need to know about the test bench, I put it on here before going to start. So here you can see the test bench. Also, yeah, you can so you can see the test bench, the module test bench, and the parameters is initialized here. And let's here this is begin and then task. So the here so here I will go to the this part a little bit later. So here you can see the clock. So it clock is you should give the clock as input to this IP, that IP that I showed you earlier. So it should initialize here. So and you can see this simulation start. So these are printing here, right? Here you can see when because I run this one. So simulation start. Those things so you need to print. You can put here because you can put any prints here in the Verilog because it is a hardware that you are going to print actually. So you can do in the the design itself, but you can do it in the code. So this kind of implementation. So here you have generate simple sequence. So it's a function like function kind of thing. You call it task here. So we have a sequence that here you can see A, X, Y, A again, A and X, Y, B. That kind of random implementation is here. So our pattern detector to check if it is working or not. Okay. So Sajid, can you share that this EDF background link is there in the chat so they can also have a look? Okay, so as I told you earlier, you can put this way open the waveform after that. So with that, you can see the waveform of this implementation. Okay, so hope you can see the waveform also. So here, this is the clock that I talked in this session. So this is the clock input. So this is the data in. Data in. These are the values. So you are wondering like why it should be A, X, Y, O, B, C, Z, like C, but the character should be there, but it shows as a value. So we can change it to binary or hex. So in here, it's easy to see in hex. So this is the ASCII value of these characters. Okay. Uh, ASCII value of these characters that we are receiving, and here you can see data in. We have if we I will describe this data in a little bit later. So you can see data out is high, not in if data out is you receive here, and there's the data out, data out, right. So states are changing also here. Before when we have four states 0, 1, 2, 3, 4. So in state 4 we get data. You see here all the data outs are in the state 4. Okay, these are all line numbers because we can't represent in state A. So this is actual ideal state, and this is state A, state AA, state AAX, and state AXY. This is all done, and this is the data out, and this is data valid signal is always 1 here. You can see if it is not this, there is no change in the data out. So that means code is not working. You can see data not change in this period. But we'll see what is this value. So here, let's say means so 59. What is hexadecimal 59? It's a y. Okay, y. So the final one is y. So if y is here, then what is 58? We will see 58 also. We can see here it's x, and previously it's 41. 41, that is value 31. Is it? Okay, so you have a x y here. Okay, because 41 is a representing a in ASCII, and 58 is x, and 59 is y. But you see only 141. What is the reason? So okay, I zoom it in. So okay, so you can see there is two clock cycles here. So first 41, then again you receive 41. That means A to 2 AC are here because you have two clock cycles. So that's why we need clock. So we can see what are the things that are going on. Okay, so 2 is 2 41s are there, and again then we have 2 A's. So then now we have X and Y based on each clock cycle. Okay. So that's it for today. So hope you guys get good uh, understanding about this. If you have any question, you can put it on the chat. I will share the code also into zip or something. Oh, it's there. Okay. So anyone who tried, and if you have any issues with this code, so you can also log into the EDA if you have previously logged into the EDA playground, so you can run it. If you have any issues, let us know here. Otherwise, over to you, Patum.
Thank you for that incredible session, sir. I'm sure our audience got to learn a lot from it. Uh, Now, as Sir said, we will move to a brief Q&A session. So if anyone in the audience needs to clarify anything from today's session, this is your time. So feel free to unmute yourself and ask anything you want. And you may also use the chat box option as well. So audience, this is your time to clarify any questions, any doubts you have regarding today's session. I will repeat. So this is the time for the Q&A session. So if anybody has any questions, we will give you, I think, 1 minute more to clarify them. Okay, it seems there are no doubts or any questions. So at this moment, I think we would like to take a moment to express our gratitude to today's speaker, Engineer Dasun Patirage, for doing a very interesting and informative session for us. Sir, on behalf of IEEE Student Branch of University of Runa, please accept this token of appreciation.
Thank you, Deshan. So thank you for inviting us, Axel. So it's well organized. So a very good number of participant count for this kind of session. So EDA to the kind of I saw like interest. There is a interest in the young young crowd in uh, first years and second year. So that's good. So once again, thank you for the invitation. Yeah.
Thank you, sir. Uh, Thank you for once again, thank you for doing a really interesting session. And uh, now it's the time to take a screenshot to commemorate this evening. So if you are in a position to switch on your camera, please join with us. Everyone, please switch on your cameras for one moment. Those who can switch on their cameras to take a screenshot to commemorate this event.
Thank you guys. All those screenshots have been taken.
Okay, thank you everybody. So now we have come to the final item on our agenda, that is the quiz. So as our participants are already aware, this will be a 10-minute quiz, and the link to this quiz, link to the Google form will be provided in the Zoom chat. And remember that all participants must do the quiz, as it will count as attendance for the e-certificate issued to all participants. And also the top 3 scores will get a valuable printed certificate. Okay, I think the link for the quiz is available in the chat. So I think we are ready, right, to start it? Guys, a little reminder. In 2 minutes, the quiz will be over. So those who couldn't submit, please hurry up. Listen, everyone, the quiz will be over very soon. So hurry up and make your submissions. Otherwise, it will not be accepted after it is closed. Okay, the time is up for the quiz. I hope everyone managed to submit it. Okay, so there we have come to the end of the final workshop of our workshop series. I would like to thank everyone who were here with us today. And we hope to see many of these faces in our physical competition, which is to be held on 10th of September at Faculty of Engineering, University of Rona. Till then, good evening and have a great week.